So we will start with question number 5. So there was a procedure that is given to determine the partition coefficient Kd of butane dioic acid. So the structure of butane dioic acid is given here between ether and water at 25 degrees Celsius. Initially, they have given 20 grams of solid BDA was shaken well with a mixture of approximate volumes of 100 cubic centimeter of ether and water in a reagent bottle. So the layers were allowed to separate. Okay, so you shake it, and normally we use the separatory funnel, but here they have used the reagent bottles, which is a typical bottle. And at this stage, some undissolved BDA was seen remaining at the bottom layer of the reagent. Thereafter, 50 cubic centimeter of the ether layer and 25 cubic centimeter of the water layer were titrated with 0.05 m in Dioic solution. Okay, and the volumes are given 4.8 and 16. Calculate the partition coefficient Kd for the distribution of butane dioic acid between ether and water at 25 degrees Celsius. Calculate the solubility of butane dioic acid in ether, given that the solubility of acid in water is 8 grams per cubic decimeter. Okay, so we'll discuss this. So let's say this is our reagent bottle. So we use 100 cubic centimeter of let's say ether and 100 cubic centimeter of water. So anyway, we have added 20 grams of BDA, butane dioic acid, and we shake it, so it will be in equilibrium. So BDA will be here in equilibrium. So BDA in ether and BDA in water, for an example. Okay. Then what they have mentioned here, they take 50 cubic centimeter from the ether. So we take this 50 cubic centimeter from the ether and 25 from water and titrate with 0.05 m NaOH. Ether is where is ether? This is they required 4.8 cubic centimeter, and water it requires 16 cubic centimeter. So you need to find Kd of BDA between ether and water. This is the what they have mentioned in the question number 1. So we will discuss that first. Right. So the first point that you need to understand here, this is very important. So this is butane dioic acid. Okay. This is of high polarity and its organic nature is very, very low. In fact, this is an organic compound, but there is only 4 carbon atoms with 2 carboxylic acids. So this compound dissolves more in water than ether. So try to identify that. Okay. This compound dissolves here more than here. Second thing, that is why they have mentioned in the ether layer, there are few amount of this BDA remaining in this ether layer. Because ether is purely organic, non-polar. But this compound is more polar than showing its organic properties. So here, this polarity is very high. So you have to understand when you get Kd of BDA between ether and water, you're going to end up getting a small value. In fact, the value should be lower than 1. Why? Because there will be more BDA in water than here. So this side becomes higher than this one, and you're going to get a lower value for Kd. Okay, that is the first point. Second point, you need to understand here the reaction is going to happen with NaOH with this one. Giving you a product, salt plus water. What is the stoichiometry between these two? That is important to understand, right? Because there are two reactable OH groups here in the butane dioic acid. You have to understand that, right? So when you react this with NaOH, this is going to be ONA. And there is water that is going to form. So what is the stoichiometry between NaOH is to our butane dioic acid? So if I want to balance this one, I have to put 2 here. So the stoichiometry between BDA and oic acid is, sorry, BDA and NaOH is 2:1. Sorry. So this is the second point that you need to identify. Okay. Then your calculation becomes straightforward. So you can multiply and get the value of the number of moles that is required here for the NaOH. So you have this 0.05 into 4.8 into 10 to the power minus 3 moles. So the BDA should be half of that one. So this should be half. And here this should be 0.05 into 16 into 10 to the power minus 3. And this should be half of it. Okay. So the number of moles of BDA here is this. BDA is this. And here BDA is this. And when you want to find the concentration, so this volume is 25. So you can divide it by 25 into 10 to the power minus 3. And here the volume is 50 into 10 to the power minus 3. In fact, you don't need to find here for 100 cubic centimeter because we need just the concentration. So you have 100 cubic centimeter solution. You take the 50 cubic centimeters, the number of mole is going to change, but concentration is not changed. Same solution, you take it, concentration is not going to change. So I'm going to find the concentration using these two directly. I don't have to find the number of moles again here and divide it by 100. I can just divide it by 50. Okay. Then I have BDA concentration in water and BDA concentration in ether. So my Kd is going to be, So first show the calculation and show the concentration. So this would be 0.05, 16 into 10 to the power minus 3. They are asking between ether and water, so I'm going to use this one first. 0.04, 4.8 over 2 into 50 into 10 to the power minus 3 divide by this one 0.05, 16 into 10 to the power minus 3 over 2 into 25 into 10 to the power minus 3. So this one cancel, this cancel, this cancel, this cancel too. So my KD is 4.8 divided by 2, then divided by 16. So in fact, my KD is 4.8 divided by 32, which is 48 divided by 320. So if I put 48 here, so it will be 6 over 4, which is 3 over 2, so 2 over 3. So you can get a value here as 48 over 320. And then there will be here like 8 into 6 is here, 8 into 4 is here. So 4 over 60. 6 over 40. You can leave it as a fraction or you can determine the value. So this question is not hard. The thing that you need to identify here is first the stoichiometry and then the calculation related to that. Then you can automatically find the ratio and get a value for this one. Okay. Give me a second to check. Yeah, that's correct. Then in the second part, I will just, so we have found this one. This becomes straightforward through this equation. Then the tricky part. Calculate the solubility of butane dioic acid in ether, given that the solubility of this acid in water is 8 grams per decimeter. Okay, now think about this for a while. So we have the KD value, which is 6 over 40 or 3 over 20, whatever it is. So now they are asking, find the solubility. BDA is going to be water in ether. So they have given the solubility is 8 grams per decimeter, right? This is 8 grams per decimeter. Now they are asking, what is the solubility here? Okay. What you know from this one is the concentration of BDA in ether. This is at equilibrium, where this is the BDA in this equilibrium with BDA solid, because some amount of BDA is remaining in ether like this. So this is a saturated condition where the concentration of BDA ether is given by this equilibrium KD. So the concentration of BDA in ether should be given here by Kd times concentration of BDA in water. Okay, because this is in equilibrium, so there is a BDA concentration in the ether layer. And this should be same when you compare the solubility of BDA solid in the ether layer, because it should maintain its Ksp value. Okay, so try to get my point. So you can write down this BDA ether concentration as Kd times BDA in water, right? So this is straightforward. So you know Kd value already. This is 6/40, or I can write as 3/20. Okay. So what is BDA water? So you can tell this is 8 grams in 1 decimeter, right? You know the volume of BDA that we used here is 100 cubic centimeter, and ether is 100 cubic centimeter. So you can imagine this is 0.8 grams per 100 cubic centimeter, because this is 1 decimeter means 1000. Or you can consider 1 decimeter of water and ether layer, because your work will be easy, because if you write 1 decimeter of water and ether, you can directly use this 8 grams per decimeter as the concentration of BDA in water, because that is the solubility in water. So here your value is going to be 8 grams per decimeter, because this is also a concentration, form of concentration. So your solubility of ether, BDA in ether, is going to be this one, 24/20, which is going to be 12/10 and 6/5. 6/5 means, I think, 1.2. What is 6/5? 1.5, yeah, 1.2. This quickly give you the idea. You see here, the solubility of BDA in water is higher than in ether, because in ether it is 1.2 grams per decimeter, but in water it is 8 gram. You see the difference. It is dissolving more in water than in ether because of this structure, because this structure is more polar. Because even if you have like CH2, 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 CH2 like butane, still it is going to dissolve in water, because this molecular weight is very low. So think about if you have 2 carboxylic acids, even though the molecular weight is high now, those are polar groups, carboxylic acids. That is why it dissolves more in water than ether. Okay. So did you understand my point here? Because this is very necessary to understand. Did you get this one? Is it okay? Did you get this one? Do you have any other questions? This is one form, like you can consider 1 decimeter. Otherwise, what you have to do is we have used 100 cubic centimeters, so you can calculate the solubility for 100 cubic centimeter, like divided by 0.8. Then you find this as ether as 100 cubic centimeters. So again, you will divide it by 10. So eventually you will end up with 0.12. So there is no point. You just have to write down this and consider for 1 decimeter, because this makes your life easier. But the explanation here that you need to understand, since there is a small amount remaining here, So there is a KSP equilibrium between these two, and there is a KD equilibrium between these two. And finally, the BDA concentration here in the solution is same, should be same from either KD or either KSP. That is what it is important to understand. Otherwise, you cannot use this equation. This equation we used here, the BDA, the solubility given by KD as well as KSP should be same. Because same homogeneous solution, you cannot have two different concentration. Because these KD and KSP are different. You cannot have same concentration. If you think like that, you are wrong. Even though KD and KSP are different, you need to have a common concentration ether maintaining KSP and KD at this particular temperature. You have to understand that point. Okay. You might think the calculation is very simple. You don't have much thing to do, but you have to understand that point because this will be helpful for your future works. Understanding that KD and KSP combined here. Very nice. Okay, it seems that you have understood. So I will share the screen again now. So this is what the part B says. Okay, so this is a simple calculation that you can do. Right, so part A is done. So part B, consider the following reaction. The thermodynamic data supplied are not for the standard states. Okay. So you have given two reaction, carbon with water giving carbon monoxide and hydrogen, and carbon dioxide with hydrogen giving carbon monoxide and water. Okay, so their enthalpy and entropy values are given. So these are not delta H theta values because they are not in the standard conditions. Calculate delta H and delta S for the reaction. 2CO giving carbon and carbon dioxide. Okay. State giving reason whether the sign of delta S agrees with the reaction taking place. Right, so we will quickly discuss this one. So we have given two reactions, right? Where are the reactions? So we have given carbon solid, water, gas, and carbon monoxide gas and hydrogen gas is formed. This is one of the reactions. The other one is CO2 gas, H2 gas, and CO gas, H2O gas. So their enthalpy values are given, enthalpy and entropy. So this is 130, 40, 140, and 50. So we need to calculate the enthalpy of this reaction. 2CO gas plus 2CO gas giving carbon solid, okay, and CO2 gas, I guess. Okay, so state giving reason whether the sign of delta S agrees with the reaction taking place. Okay, so we will need to conclude about the entropy as well. Okay, so this is the reaction. So how do you going to approach this one? What do you think about these two reactions? And with the overall reaction? What do you see? We have discussed this type of question before, if I can remember, 2012 maybe. because this is the reaction that they have given. So we need to find delta H and delta S here, right? You need to get 2CO. I see CO here and CO here. And if I want to end up getting 2CO, I need to add these two reactions together. So if I try to add these two reactions together, these two, so I am going to end up here with 2CO solid. And this hydrogen and this hydrogen is going to cancel out. And this water is going to cancel out. So I am going to remain with carbon solid and CO2 gas. So what I see here is the reverse of this reaction. The reverse of this reaction. Right? So that is one thing that I see from this reaction. There is a connection between these two and I get the reverse. Right? But my point here is you have this CO here. You have this carbon and carbon dioxide here. Right? So we will try to analyze this one. Okay? In order to get certain products. For an example, I have carbon here. And there is a reaction happening with carbon. I know the enthalpy and entropy values of this reaction. Right? So when I have carbon here, and if I have water, I can obtain carbon dioxide, carbon monoxide, and hydrogen. So I have carbon here, but I don't have water here. Instead, I have carbon dioxide. But it doesn't matter. I can add water here, H2O gas. And I know when this carbon solid and H2O gas react, carbon solid and H2O gas react, I am going to obtain carbon monoxide and hydrogen gas. But there is additional thing which is not going to react, that is carbon dioxide, which I am going to put like this. Okay. And same here, I have CO here. Where is CO? This one. And I have completed this reaction now using this one. So I am remaining with combining this reaction to this scheme. Right? So I have CO here. So where is CO? CO is here as well as CO is here. So in order to balance these two sides, if I add water here, I have to add water here. But I have to check adding water makes sense of adding this reaction to this cycle. Because I have to check CO, here also CO, here also CO. But this reaction is already covered. So I have to just think about this reaction. So CO with water, okay, CO with water gives you again CO2 and H2, which is here CO2 and H2. And CO, one CO is remaining. You see, only one CO is reacting. One CO plus H2O giving CO2 and H2. One CO is remaining. So this becomes a cycle now. Because this H2O and 2CO. So H2O and 2CO, only one CO is going to react. That is why here there is only one CO here. So H2O and CO, this enthalpy and entropy values you already know, because it is the reverse of the given value. And here you know, when CO2 reacting with carbon reacting with water, CO gas and H2 is going to form, which is my first reaction here. This is also enthalpy and entropy values are you know. But here it is not the reverse. Not reverse, because my arrow is this way. If I put the arrow towards this direction, like this, now it becomes the reverse. Okay, try to get everything, every point of the enthalpy cycle, arrow reversing, sign change, balancing equations, and everything from this example. Okay, so this is the equation that they have given you. But what I have tried here is trying to manipulate this equation by adding water to both sides, so that I am going to end up reaction that is given here in my data. Because if I have given those data, I can easily calculate enthalpy of this unknown reaction. Okay, so here delta H and delta S is the reverse of it, because here the reaction is between one CO and H2O, one CO and H2O giving carbon dioxide and hydrogen. That is what we have seen here. So this is the reverse of it. So basically from the first equation, so where is H2O and where is CO? So this is this one. So this one is the second equation. So this value is 40 here, enthalpy. So this could be minus 40 and minus 50, because that is the reverse here. And here, if I change the sign here, so again, it is going to be the reverse here for the first reaction, where carbon and water is going to react from CO and H2. So this is going to be minus 130 and minus 140. Right? So if I want to get the enthalpy, so delta H is according to Hess's law. This delta H is going to be sum of these two, which is minus 40 and minus 130, which is minus 170. And when you get the entropy, it is going to be minus 150, minus 50 and minus 140 is minus 190. So entropy is negative. You see, entropy is also, I would say delta S is negative according to our calculation. But they say one additional point to mention. So in the question, they say, state giving reason whether the sign delta S agrees with the reaction taking place. So I'm going to take delta S, the value of delta S as a negative value according to the calculation, and whether they say this is agreement, in agreement with our reaction taking place. You can automatically see here, this is a gas. This is a gas. But don't forget, there is a solid product that is formed. So when there is a solid that is forming, what happened to the entropy? It is decreasing. Because initially you have only gaseous products. But here you have gas plus solid. So gas, again gas, it's okay. So entropy is nothing much change. But when there is a solid that is forming from a gas, your amount of randomness is going to decrease. which gives you the idea the entropy should be negative. So when you get entropy as a negative value, so you can mention it is in agreement with the reaction taking place, because a solid product is formed from gaseous reactant, which gives you the idea the entropy is even reduced. That's the idea that you need to understand. Okay. The second question of that part says, by means of suitable calculation, predict whether the reaction given in part 1 above is spontaneous at 27 degrees Celsius. So what you have to do, you know the delta D is equal to delta H minus T delta S. Okay. So you can put the delta H and delta S values for this particular reaction, and you know the temperature. Then you can calculate delta G, and you can check whether this reaction is spontaneous or not. That is how you can do. So that is very simple. Second part of the question is very straightforward, that you can calculate. So when you do the calculation, you will see the delta G value is minus 113. So we know the delta H values and delta S values. That is minus 170 here and minus 190. So delta H is minus 170 and delta S is minus 190. And when you plug these values, minus 170 here, temperature 27 means 300 Kelvin. Delta S is minus 190 into 10 to the power minus 3, because it is given in joules, so you have to convert that into kilojoule. And when you find delta G, you will get this is minus 113 kilojoule per mole. Okay, so think about this reaction more and more. Okay, so delta H is negative, so you might think this reaction is spontaneous, I mean from the beginning. Then delta S is negative, so you might think this reaction is not spontaneous according to entropy, because it forms solid product. But in fact, when you find delta G, you see it is a negative value, so this reaction is actually spontaneous. So even though the entropy is decreasing, you can see here, according to the piece of information that they have given, this reaction is spontaneous. Okay, but don't forget, these are not standard conditions. That is the important part. Okay, so they have tested you, and this is very nice piece of information to understand and analyze more and more. So when you have a question like this, because you are studying, you are not just doing any exam, so you do this question, you get an answer, don't stop there, try to analyze more. So what piece of information that I can get, what I can predict more, what I can expect more. So these are the things that you need to understand and analyze. We say deep analyze. Okay, so this is how this calculation can be done easily, right? Right, so we will move on. So this is done then. Right, so question number part C is again straightforward there. So an excess amount of carbon solid and 0.15 mole of CO2 were placed in a closed rigid container of 2 decimeter, and the system was allowed to reach equilibrium at a temperature 689. Once the equilibrium was achieved, the pressure of the container was found to be 8 into 10 to the power 5. So this is total pressure, which is PT. and write an expression for the equilibrium constant Kp. So we have the reaction, let's say, so we have the reaction that they have given carbon solid plus CO2. So carbon solid plus CO2 gas is in equilibrium, giving 2CO gas. Okay, so this is going to give 2CO gas. So you have given RT value, take as 8000 joules. Temperature is given, total pressure is given. So write an expression for equilibrium constant Kp. So you know here there are two gases, one solid. So your Kp is going to be only the gaseous products because Kp is related to pressure. So pressure of CO gas to the power 2 over pressure of CO2 gas. Okay, so this is going to be our Kp expression. Calculate Kp and Kc at 689. So how do you do this? So according to this piece of information that they have given, initially they have used 0.15 moles of CO2, right? So this is excess. So at equilibrium, this could be 0.1 minus 0.15 minus x, and this could be 2x that is formed. So if you use this PV equal to nRT equation here, pressure is known, which is our total pressure that is given here in the question. That is 18 to 10 to the power 5. So this is 18 to 10 to the power 5 Pascal. Volume is given 2 decimeter. So I have to put that in meter cube. And NT at equilibrium, you have to find, because if you know NT, you can find X here, and you can count the remaining amount of carbon dioxide and CO that is formed. So RT, they have given, take that as 8000 joules. So I am going to get this as 8000 joules. So, sorry, ANT is going to be, here there is a 10 to the power 2 factor that I can cancel with this one. And here there is 16 over 80, right? Because 18 to 2 is 16. So I have 10 to the power 2 here. I cut with this one, yeah. So this is 1 over 5. So 1 over 5 is 0.2 moles, right? This is 0.2 mole. If I am correct, my calculations are correct. And you know, NT at equilibrium, NT at equilibrium should be 0.15, right? Minus 6 plus 2x, because it's the sum of these two. So I'm going to end up with 0.15 plus x. And this is equal to the amount that obtained here from PV is equal to nRT, 0.2. So I am going to get x as 0.05. Okay, so if x is 0.05, so at the end of my reaction at equilibrium, basically, I am going to get here as 0.1. And here this is 0.05 into 2, which is 0.1. So that is how we got 0.2 total moles, 0.2. Then what I can do is find x mole fraction of CO2 gas, which is now going to be 0.1 over 0.2. And this is also going to be equal to the mole fraction of even X CO gas as well. because same amount is there. Then you can write down the partial pressure of CO gas, which is the total pressure that is given here. So it will be 8 into 10 to the power 5 according to the Dalton's law. Partial pressure is equal to mole fractions time total pressure. So this is 1 over 2. So according to this calculation, so this is going to be equal to the partial pressure of CO2 gas as well. So this is 4 into 10 to the power 5 Pascal, right? So this becomes very simple calculation. You see, I did this in very simple way, even it is hard amounts. So then you can apply here in the values for this pressure, and you can get Kp. Then finally, then you have the equation. First, you can calculate delta N here. So delta N is 2 moles of gases, 1 mole of gases. So 2 minus 1 is equal to 1. So you can use Kp equal Kc RT delta N to calculate Kc. So that is what they have asked here. So you can calculate Kp and Kc at 689. Okay. Right. So the last part. In another experiment, the container described above contains an excess of carbon. Okay. So anyway, here also they have used excess carbon together with CO and CO2. So initially here in this reaction above, they have used 0.15 moles of CO2 only with excess carbon. But here they are turning it little bit, manipulating it, okay? And they have used CO and CO2. And the initial pressure of each gas, they have given the initial pressure of each gas. So this is 2 into 10 to the power 5. And this is also 2 into 10 to the power 5. Explain with the aid of a calculation the change in partial pressure of CO2 gas when the system reaches equilibrium. Okay, so here I will use my whiteboard to explain. Okay. Right, so the reaction was very simple. Carbon monoxide gas, CO2 gas. In fact, 2 moles. If I can remember, let's see. Yeah, it's the other way around. Okay, so at 689 degrees Celsius, whatever the temperature, we found that Kp is equal to 4 into 10 to the power 5 Pascal squared over, because we found according to the PV equal nRT and mole fraction and all those calculations, the partial pressure was 4 into 10 to the power 5. So this is 4 into 10 to the power 5 of 2, and this is 4 into 10 to the power 5. So you can cut this. So Kp at equilibrium was 4 into 10 to the power 5. But don't forget, this case was carbon solid, CO2 gas, 2 CO gas. So 0.15 initially, finally 0.1, 0.1. Right? Now, in the second case, what they are telling here is they have used some amount of CO2 and some amount of CO. And their initial pressure, 2 into 10 to the power 5, 2 into 10 to the power 5. And they are asking to predict whether what happens to this pressure of CO2 and CO when it reaches equilibrium. Okay. Now, this is where comes my reaction quotient RQ. Okay, because although you change this CO and CO2, or you add some amount or you remove some amount, at the same temperature at equilibrium, your Kp has to be this one. because temperature is constant. Either you start with 0.15 moles of CO2, or either you start with 0.15 moles of CO2 and 1 mole of CO. It doesn't matter because Kp should be finally this. Okay. Now this pressure is given before equilibrium. You remember we calculate RQ in KSP before the solution gets saturated or before precipitate forms. This is type of a same condition where we calculate a Q, RQ, reaction coordinate. That is before equilibrium, which means in the pressures that they have given. So for an example, according to our RQ expression, so this should be 2 into 10 to the power 5 Pascal squared over 2 into 10 to the power 5 Pascal. So you can cut one. So I have my RQ as 2 into 10 to the power 5 Pascal. So this RQ value should go from here to here, which means this should increase. At equilibrium, to reach equilibrium, my RQ value should increase from 2 into 10 to the power 5 to 4 into 10 to the power 5, which gives the idea in this equation, the equilibrium should shift towards the right hand side. Why? Because my Kp expression is this pressure squared over this. So in order to increase this factor here 2 to 4, this side should have a higher value and this side should have a lower value. Therefore, the partial pressure of CO2 is decreasing, the partial pressure of CO is increasing. Okay. So what you can do here is you can simply find RQ and tell this value is smaller than our Kp. So in order to increase, in order to achieve Kp equilibrium, the Kp should be 4 into 10 to the power 5 at the same temperature. So that to change this RQ towards Kp, the equilibrium should shift towards the right hand side, making the concentration of CO2 drop and increasing concentration of CO2. Okay. This is only one method that you can explain. Otherwise, you can do some other calculations as well, like taking the initial pressure as this, and you think that the final pressure is this 2 into 10 to the power minus x, and here you put 2 into 10 to the power 5 plus 6, and you solve the quadratic expression using this Kp value, and you show that either one of the x is values, and you show that CO2 is decreasing and CO is increasing. You can do that also. Okay, you can do in this way. This is the simplest way. You calculate RQ and you explain using the terms. That is very simple in order to get quick answers. Otherwise, what you can do here, you write here 2 into 10 to the power 5, and you put here minus x into CO2 side, and here you put plus 2x into CO because stoichiometry is 2. Then you use this value because these are the final pressure values of these two CO2 and CO, and you plug this in the Kp expression where your Kp is 4 into 10 to the power 5. Then you find finally x and show here CO2 is decreasing and CO is increasing, the pressures. You can do that. But as you wish, you have to find a simple way, and I have explained this very simple way. Okay, so I hope you have understood this. Right, so what is the change? The partial pressure is of CO2 is decreasing while the partial pressure of CO is increasing. That's the idea. So this question number 5 is done.